So types of chemical reactions, empirical molecular formula, balancing, anything else? That's a pretty good list to start off with. All right. We'll get started soon, and you guys could just keep asking questions, and I'll just keep adding to the list. But seems like a pretty good list so far. All right. Types of stoichiometry. Stoich. All right. Types of chemical reactions. There are 5 of them that you have to know. So there is decomposition. There is synthesis. There's single displacement slash replacement. There's double displacement. And also combustion, fire. So you just need help like making the equations for this stuff. So I guess we should first talk about what each of them are. So decomposition is when a big molecule or big compound, it breaks up into its constituent parts. So smaller individual elements. Synthesis is the exact opposite. It's smaller compounds. They form together to make a larger compound. Almost like fission and fusion, big compound. Someone says, will there be 2 elements with, let's just say, decomposition? I struggle with that. 2 elements with decomposition? What? What does that mean? Whoa, that's what I just said. Nice. Single displacement is hola. Single displacement would be where you replace one similar part of a compound. I don't know what 5b is on the homework, so you're going to have to type it out. Double displacement is you're basically switching similar parts of compound. And then combustion, you're just letting it burn. In the presence of O2, and the usual products that you'll make is CO2 and H2O. And then what? You just want some questions on how to make these? Let's see, do I have any practice problems? I guess that's it. I think everyone can hear. So that looks like a Stoich problem. So we'll get to Stoich after the other stuff. All right. Stop pretending, Mr. Lee. What? Stoic named after someone because if I had Stoic as the last name, that would be very Matt Stoic. Stoic, stop pretending. Says he's talking. Hi, Michael. Hi. What's another one? Oxford. All right, it's ready, set, go. Blah blah. Is he talking? Hi, hi. Oh man, can anyone hear? Am I just getting tricked? It's all Mr. Lee, so he's pretending to be frozen. So there's no potential here. Stop flexing, flexing. You can speak equally as well. Andrew Energy, you were in my class last year, Matt. What's happening? Yeah, she. Kenny is not here. Sorry, I was just typing stuff. I was trying to make up problems for you guys, so there's no reason for me to be talking. If you guys can hear me, type potato. Alright, you guys can hear me. Unless you're really good at reading lips. Alright, do the problem. Write balance equations for the following reactions, including states, and then also identify the type of reaction. Do you guys want actual time, or should I go through each of them? Who's Emma K? Wait. Go through each one. Go through, please. Huh? Each. What? Add each. This was my downfall today. I passed my test. Why are you Emma K? Isn't your last name Stowball? Middle name. Gotcha. Well, you're gonna be you have to take a quiz. All right. Let's do these. F2, N2. Ooh. Actually. Whoops. First one's impossible. Who can tell me why the first one is impossible? Yeah, there's no hydrogen. So let's change fluorine to hydrogen. Close, but no cigar. So hydrogen definitely is a diatomic, so it's going to be H2, and it's a gas. Combines with nitrogen, also diatomic, and a gas, to form hydrogen nitride gas. Hydrogen is a +1 charge, nitrogen is a -3 charge, so then it would be, that's not it either, Michael. That's hydrogen nitrate gas. So like this, so this would be your very first thing you do. Just write out the compounds in the sentence, and then you would go back and balance. You're like, all right, I have 2 hydrogens here, 3 hydrogens here, nitrogen, nitrogen. So like, hey, look, I have 2 nitrogens. How can I point? I have 2 nitrogens here. I only have 1 nitrogen here, so 1 and then 2. So that if I put a 2 in front of here, my nitrogen is now 2. So we're good. Now I have 6 hydrogens. I need to get this to 6, so then I put a 3 here. And then now it's balanced. So 3H2O and 2. And what type of reaction is this? This is good synthesis. So next one, C4H10. That is a butane gas. It burns. So C4H10 gas burns. So hey, Mr. Lee, you didn't give us enough information. You guys should know, in order for something to burn, what other reactant does it need? Yes, it's combustion. It needs oxygen. So we have to add plus O2 gas. And what are the main products that you can make from combustion? H2O is one of them. And CO2. Nice. Then from here, you just have to balance. Okay, I have 4 here, 10 here, 2 here, 2, 1, 1, 2. So first thing I like to balance are things that are not hydrogen or oxygen. So I'll look at this. I have 4 carbons and only 1 carbon here. So if I put a 4 here, this changes it to a 4, and this changes it to an 8 oxygens. Then I can look at my hydrogens here. I have 10 hydrogens, only 2 hydrogens. So by putting a 5 here, that becomes 10, that becomes 5 now. So then I have to add up my oxygens. So I have 5 oxygens plus 8 oxygen. That's 13 oxygen. So it's like, all right. If I actually look, there's 2 oxygens and 13 oxygens. Is there actually any way for me to get an odd number with if my O2s always come in a pair? No, there's no way, right? And for crucial, do you see any like key word that lets you know that C4H10 is a gas? Yeah. So there's two ways to do this. You can realize there's actually technically three ways. One of them is just guessing and checking. The guessing and checking method is, hey, this didn't work out. My balancing didn't work out if I just had one right here. So it's definitely not one of these. So then the next thing you could try is 2, 3, 4, 5 until it works out. But I'm not a big fan of guessing and checking. So what I like to do is I realize technically I just need 13 oxygen atoms. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, like that. So 6 just oxygen atoms by themselves. So there is a way for me to get 6 oxygen atom or 13 oxygen atoms. Why did I say 6? 13 oxygen atoms from this, but it's by using a fraction. What fraction would I use to get 13 oxygen atoms on my left side? I would need a half somewhere, but if I just did half right here, I would only have one oxygen atom. But I want 13. Yeah, 6.5. So I like to do fractions. 6.5 is 13 over 2. But here's the thing, you can't have fractions in your final answer. But if you actually look at all of this, let's get rid of some stuff. Is there an eraser? Or. Yeah, you eventually can multiply everything by 2. Alright, don't know what eraser is. I'll just write over it. So then, different color. We want to get rid of that 13 over 2. To get rid of that 13 over 2, I use greatest common multiple. Hopefully the least common multiple, because technically there is no greatest common multiple, because it'd be infinite. So then, multiply everything by 2. That becomes just 13. This becomes a 10. This becomes 8. Yeah, so in your process, you could have fractions. Then you just have to get rid of your fractions by the end of it. Another way that you could do it is what Kushal said is the least common multiple. So let's pull this out again. So if C4H10 plus O2 makes CO2 plus H2O. Up and now we got what? 4, 5. So we're stuck at there's 2 oxygens and then there are 13 oxygens. And between these two numbers, so what Kushal is saying, you can find the least common multiple. Yeah. What's the least common multiple between 2 and 13? 26. So how do I get 26 here? What do I have to multiply the 13 by? 2. I have to get to 26 here by multiplying by 13. So the easier one to do is to, this is going to get, actually, does least common multiple work here? Technically it does. So yeah, so I put 13 there. So let's use a different color. So 13. So now I have 26 oxygens. I somehow to get 26 oxygens on this side. So yeah, this part gets tricky. So you have to make 26. So you have 8 right here, 5 right here. That's 13. I have to get to 26. You have to mess around with some numbers. It's hard because I already know what the answer is. But how would you guys go about it? You need delta for this problem? No. Eventually this just becomes 10. This becomes 8. because then you get 16 oxygens from carbon dioxide and 10 oxygens from the water. Total of 26, but then you just have to change this to a 2. Yeah, I don't know how you would get this problem. It's trial and error. So because you wrote heat instead of delta on the quiz, it's probably the same. It's fine. But yeah. So this balancing problem is a little bit more difficult balancing problem, but technically you should still be able to do it. You just use fractions to do stuff, so let's not get carried away. So then the next problem is, oh gosh, that's not too lacking. Let's get rid of all of this. Nope, that's not what I want to move. Well, I'm just breaking stuff now. I'm like freezing up. Wrong again, Michael, but thanks for being confident in typing in your answers. We appreciate your confidence. So I'll just write it again. Iron 3 oxide decomposes. So this obviously is a decomposition reaction. So iron 3 oxide is going to be Fe2O3 solid decomposes Fe solid plus O gas, but you should remember that you never have fear of ice clear beverages, diatomic. So then at this point you just have to balance. You have 2 irons here, so you put a 2 here, so your irons are good. 3 oxygens here, 2 oxygens here, so crucial. So remember, there's 2 ways of doing this. You could either no. You could guess and check. So at this point, you figured out that, hey, having one of these didn't work out because these don't work out that well. But then, so then you could just try a 2 here and then see if it works out. So that's just the guessing and checking method. The fraction method, or let's go with the least common multiple method. Least common multiple between a 3 and a 2 is 6. So that means you eventually want 6 oxygens on both sides. To get 6 oxygens on both sides, you need to put a 3 here. That gets you 6. And you need to put a 2 here. But that changes your iron now. So now you have to change that 2 to a 4. So states of compound. You forgot the solid liquid gas stuff. I didn't forget the solid liquid gas stuff. You forgot the solid liquid gas stuff. Because I definitely have an S right here for solid, S right here for solid, and G right here for gas. How do you know if it splits into 2? I'm in Savannah. Oh, gotcha. Bro, don't be like that. So how do you know it splits in 2? Because in the problem I said that iron 3 oxide decomposes. So decomposition reaction is a big molecule breaking up into its constituent parts. So the iron and oxygen, like that. So that's how you know it broke up into 2 things. And how you know states of matter, because in our notes we said that H2O will most likely be a liquid. Carbon monoxide will be a gas. Carbon dioxide would be a gas. And in our notes, we said the rest solid. And if they're elements, you should know. Pretty much all of them are solids. 2 are liquids. Which 2 are liquids at room temperature? One's a metal, mercury, and then bromine. Those two are liquids at room temperature. Then the gases are your group 18, noble gases, and then Fonkel, F2O2, N2CO2. Those are the four gases, or gases. All right. And then the last one, sodium hydroxide reacts with cobalt 2 fluoride. That's too much for me to remember. Why do you think, Kushal? Why do you think you don't have liquid water when it's fire? Perfect, Michael. Thanks for answering his question. Because if you think about it, if you started making a fire and then liquid water started to form, what's going to happen to your fire? It would extinguish. So literally every time you start a fire, your fire would get put out by the water that forms. Sometimes. I think that's how it would work. But essentially, it's vaporizing it, so the water vapor is coming off. Yeah. Cool. All right. We spent 26 minutes talking about types of reactions. Kind of talked into balancing, so we'll come back to balancing. 0 to 27 minutes. Types of reactions. Yes, Matt. Empirical formula is definitely next. So empirical formula. So here's the difference between empirical formula and molecular formula. An example would be a molecular formula is 22 out of 55. That'd be your molecular formula. So like 55 students, 22 of them are boys. So that'd be your molecular formula. Your empirical formula would be 2/5 boys, students. So your empirical formula is just the simplified version of your molecular formula. And it keeps the same ratio. The ratio is always going to be 2 to 5, or 2/5. Same with this. And that's the same ratio. So for an empirical formula, you could have something like CH2O, meaning for every one carbon, there's going to be 2 hydrogens and 1 oxygen. So the ratio is still the same. So that if we go to the actual formula, it might be like 6H12O6. So it's 6 times bigger. But if you look at it, the ratio is 6 to 12 to 6, which reduces down to 1 to 2 to 1. So the molecular formula is the actual molecule. The empirical formula is the simplified version. So if I had a class of 55 students and 22 of them were boys, this would be my actual class size, 55. But if someone asked me, hey, what percent of your classroom is boys? Typically, I won't say, oh, 22 out of 55. I'd say, oh, about like 2/5. So that's my empirical formula. It's just that this is 11 times larger. So that's all that is. Yeah, it's like a simplified ratio. So instead of having like a 6, 12, 6, you could reduce it down 1 to 1. So that comes into play when we have to find molecular formula given an empirical formula. So let's do a problem. So I guess I should do steps. Typically for empirical formula, what we'll give you percents. We're going to say, hey, here's this compound. It's going to have like, I guess I should just show you guys a problem. All right, this one. We have 14.87% phosphorus and 85.13% chlorine. So you have this random chunk of whatever, and it tells you, hey, 14.87% is phosphorus, and the 85% is chlorine, somewhere in this molecule. So what you want to figure out is, all right, I want to know the ratio of all this. But anytime in chemistry you find ratio, typically you almost always will be finding the mole ratio. Meaning, what do we have to find? Yeah, you have to find the mole. You can always assume it's a 100-gram sample because you're just given a percent. So it actually doesn't matter how much you have. No matter how much you have, the ratio will still be the same. So it doesn't matter if you say, let's assume 17 grams, but if you do 17 grams, you have to find 14.87% of 17. So that's why we just do 100, because if we assume it's 100 grams, super simple. So what you just do is assume 100 grams. So that math is a little bit easier. So now you say, okay, assuming I have 100 grams of this stuff, that means 14.87 grams will be phosphorus and 85.13 grams will be chlorine. So then remember, we want the mole ratio. So the first part of mole ratio is a mole. So let's find a mole. So you have to convert these to moles. So I want to get rid of grams of phosphorus and go to moles of phosphorus. Mr. Mole's favorite number is 1 when he's by himself. And we don't use phosphorus enough for me to know it. 30.97. Grams of phosphorus cancels out. This becomes 14.87 divided by 30.97. Let's store that in a like 3 or 4. But then if you tell me you store it, then you just say, oh, I stored this in A. Then for chlorine, I know chlorine, we use it a lot. So grams of chlorine, moles. Chlorine, Mr. Mole's by himself, so he gets 1. Grams is 35.45. 85.13 divided by 35.45, we get, yeah, that should be fine. 2.401 dot dot dot, and I'll store this in B. So now you have moles, but I want a mole ratio. What kind of math do I have to do for a ratio? Division. Never round in between your steps, because if you round, things could get ugly. So ratio, you're going to divide, and you always, anytime you divide by your smallest number. Smallest mole. That's why if I go back real quick, if I look at this C6H12O6, how did I go from 6 to 12 to 6 to 1 to 2 to 1? What did I divide each one by? 6, which was my smallest number in that case. Yeah, the greatest common multiple. Good. So then in this case, it's kind of convoluted. You can't really figure out what the greatest common multiple is. So we just tell you, hey, divide by the smallest number. So then in this case, we would just divide by 0.480 dot 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 0.480 dot dot dot. That first phosphorus is obviously going to become 1 phosphorus, right? We need 1 phosphorus. But for the chlorine, we need, it says it's 5.001 dot dot dot. Is 5.001 pretty close to a whole number? Is it within 0.2 of a whole number? Yeah, so then we could just assume that we need 5 chlorines. So my empirical formula would be PCl5. But, adios. The second part of the question that I could always give you, something like, all right, the molar mass of the molecular formula is 1665.76. What is that? Grams per mole. I want you to find the molecular formula. So remember, my molecular formula is going to be some version bigger than my empirical formula. I just have to figure out how many times bigger it actually is. So in order to do that, we compare their masses. We see, okay, how much bigger is it? So what you have to do is the molar mass of the molecular formula divided by the molar mass of your empirical formula. This number will give you how many times bigger your molecular formula is. So molecular formula should always be given. So in this case, it's 1665.76. How would I find the molar mass of the empirical formula? Yeah, you add up all the individual masses of your empirical formula. So the molecular formula is like your actual molecule, like C6H12O6. But then your empirical formula is like the simplified version. So it's like instead of writing answer as 4/10, the simplified version would be 2/5. So we compare the molar masses. So we just want to know how many times bigger it is. So we want to know, okay, how many more phosphoruses do we need? How many more chlorines do we need? And we can figure that out by just comparing their molar masses. So if I add up the molar masses, yeah. So then the molar mass of my empirical formula is 208.22. So now I compare. Hey, this was my molecular formula. This is my empirical formula. How many times bigger is it? This should always come out to pretty close to a whole number. And this one is 5. So that means the actual molecule is 5 times bigger than your simplest formula. So that to get your molecular formula, you need P5 ACl25. So it's like this would be the actual molecule that you would have. The empirical formula, you just reduce it down to its simplest formula. Let's see if I could come up with a problem that does not. All right, let's try to think of something. Me? No. I'm just trying to think of a problem where it doesn't come out to a whole number. So I just think of some percentages. Let's do something like NO. Let me scratch paper. Not necessarily. If you don't get a whole number at this point, then you probably messed up somewhere. This point right here. When you're dividing it, this should always be a whole number. If this number is not a whole number, like 5 or like 4.99998, then you probably messed up in your empirical formula somewhere. Let's see. Let's try to make this formula so it's like this. That means the mole ratio 2, 1. Two. All right. Wait, will that work? Look at me trying to come up with a problem. Might as well make this a test question. Put it on there. 16. Perfect. It works. Oh my gosh. All right. Who asked for this problem? Making my life difficult. All right. So, oh shoot, I forgot the percentages. 1.9 plus 1.6 divided by. Nope. No, divided by 3.5. All right. 63.2% is nitrogen. That means the 36.8% is oxygen. Find the empirical formula given that the molar mass of the molecular formula is, I wanted that. 684.20 grams per mole. 63.2% nitrogen, 36.8 oxygen. I'll give you some time to try it out. This problem that I had to create from scratch. Thanks for giving us so much molar weight. No problem. Google's a great calculator. What time does before school help start at? Whenever I get there. Typically around 7:10. You're always welcome to come. Should I go over it? Or do you guys want more time to actually try it out? Yeah, 63.2% and 36.8%. No, 63.2%. All right, more time it is. Yeah, you guys better work hard on this problem that I made. You have to be more specific with your questions, Kushal. Actually, I don't even know what the answer is. I should do this problem. Wait, this doesn't seem like the problem. Ah, this is not the problem I thought of, but it works. Oh, that's why. Whoops. Good job, Michael. You're right. It is N2O. But let's switch some stuff around so that we make it a little bit more difficult. Let's switch it. O and N. But yeah, Michael, you were right. It was N2O. But that's not what we wanted. You guys wanted a practice problem where the mole ratios wasn't roundable. So converting to grams to moles of CuCl, do you use 0.4027 or do you use a few digits, similar to empirical formula? 0.4. All right, I think I will do this problem, unless anyone objects. Are you objecting? All right. I guess we'll vote. Michael says he wants more time. Who else wants more time? More time. All right. More time. All right. This is the longest GBL. We've only done 1.5 topics. So I guess I'll write out the steps for you. Step 1. Assume 100 grams. So change the percent symbols just into grams. Step 2, convert grams into moles. Step 3, find the mole ratio by dividing by smallest mole. Step 4, if within 0.2 plus or minus whole number, then you round. If not, multiply by 2, 3, 4 until true. Nitrogen. But good, it is N3O2. That's what it should be. And I did make it times 9. So I was thinking where if it's 0.25, 0.75, you multiply by 4. Yeah. So let's go over this. So that just means, so we'll talk about this. So we have 63.2% oxygen. So I'm going to assume 100 grams. I'm going to change that just to grams of oxygen. I want to get rid of grams of oxygen, go to moles of oxygen. Mr. Mole's by himself, so he gets the 1. And 1 mole of oxygen atom, 16.00. Then 63.2 divided by 16 gives me 3.95 moles of O. Then I have 36.8 grams of nitrogen. I want to get rid of grams of nitrogen. Go to moles, nitrogen. Mr. Mole's by himself, so he gets a 1. 1 mole of nitrogen atom is 4.01. Then you get 2.626 dot dot dot. So then, who's asking some questions? What do you have to do with these moles now? What am I trying to find? A mole ratio. So mole ratio meaning I have to divide, and I have to divide by the smallest mole. In this case, the smallest mole is 2.626, so 2.626. That will make me 1 mole of nitrogen. Divide this by 2.626. And you get 1.503 moles of O. So whoever asked that within 0.2, so if you notice, 1.5 is not within 0.2 of a whole number. It's 0.5 away from a whole number, so you just can't round. It's not close enough for you to round. So now what you have to do is, all right, first thing I'm going to try is multiplying it by 2. If I multiply this by 2, this becomes like 3.006 dot dot dot. So hey, that means I want 3 oxygens. But then I have to multiply this by 3 to get 3 nitrogens. You have to multiply because it's like saying you can't have half of a shirt, right? If you have half of a shirt, you can't go out and buy half of a shirt. So that means you would just have to double everything and say, okay, the bare minimum I would need is 2 full shirts or 1 shirt, like that. So you need to have that ratio be closer to a whole number. Yeah, it's kind of like you're balancing the equations, but instead of an entire equation, you're just trying to kind of balance a formula, one compound. So then my molecular formula would be N3O. Nope. Whoops, I multiplied that by wrong thing. 2 nitrogens. Because I multiplied this by 2, I have to multiply this by 2. So this would be N2O3. Then if I compare the molecular masses, the N2O3 would be 14.01 plus 14.01 plus 48, 76.02. Then if you compare this, the molar mass of the molecular formula, and then the molar mass of the empirical formula, you divide these two numbers and you get, hey, my molecular formula is 9 times bigger. So then it would have to be N18O27. So that would be my molecular formula. 0.2 is close enough to a whole number. 0.3 is still kind of too far because you could have a third. That's just like that good number that if you're within 0.2, you're close enough for it to round. Because if you double one part of your recipe, you have to double your other part of your recipe. So if you multiply one of them by 2, you have to multiply all of them by 2. Yeah, so 1.2 would be 1, 0.8 would also be 1. Phew, that's empirical formulas. No, be nice. Yeah, so when you divide your molecular formula and your empirical formula, that one should always be pretty close to a whole number. In this case, I think I messed around the number so that it wasn't a perfectly whole number, but I made it really, really, really close. It's like 9.00026,308, like that. All right, that's about an hour. Empirical formulas and molecular formulas. Balancing. I'm going to put balancing as a part of Stoich. Conversions. Well, conversions, I'll just do it separately. Conversions you should know how to do. So, what I like to show my students is Mr. Mole's neighborhood. Welcome to Mr. Mole's neighborhood. Mr. Mole is the most important, so here's Mr. Mole. And Mr. Mole's favorite number is 1, so he likes to have a 1 in front of him. Next to him lives group of atoms. Group of atoms. And your groups of atoms could be two things. They could either be molecules or they could be formula units. The math is exactly the same, it's just that the unit changes. And on the other side of Mr. Mole lives good old Grandma Graham. Then you get to total atoms. I should redraw this. So I'm going to use a thinner pen. So we have mole, goes next to grams, goes next to groups of atoms, so either a molecule or formula unit, and then lives next to total atoms. So this is pretty much how you convert from one thing to another. And then anytime you go between moles and grams, you have to use the molar mass from the periodic table. Anytime you go between moles and molecules, 6.022 times 10 to the 23rd. Then anytime from a group of atom molecules or formula units to atoms, this you have to count the number of atoms in one of these, in one molecule or one formula unit. So that's really it. So I had this on my board in my class for the entire unit. Very important. So I could give you any random problem now. I could say, hey, convert, or how many grams are there in So how many grams are there in 5.67 times 10 to the 24th 4 millunits of calcium chloride? So what I like to do is draw myself a roadmap. You think to yourself, okay, I'm starting at formula units, and I eventually want to get to grams. So then I'm basically starting from here, and I want to end up here. So whose house do I have to stop by? Yeah, mole. So that means from formula units, I have to go to mole, then I could go to grams. So moles to grams, I'm going to have to use my molar mass. And from formula units to moles, I have to use Avogadro's number. So now I have my basic outline of where I'm going to go. So I'm starting with the number 5.67 times 10 to the 24th formula units of calcium chloride. And I want to get rid of formula units of calcium chloride and go to moles. Calcium chloride. Since Mr. Mole is by himself right now, he could get his favorite number 1. And hey, look, I'm going between formula units and moles, so I have to use Avogadro's number. So now my formula units cancels out. I'm at Mr. Mole's house. I'm stuck here. But I eventually want to get to grams. So next stop, I have to get rid of these moles. So I put moles on the bottom. And I want to go to grams. Grams of CaCl2. Mr. Mole's by himself, so I could put a 1 there. Then I have to add up calcium and 2 chlorines. That is the molar mass. Moles, calcium cancels out. Stuck with this, times 5.67 to the 24th, divided by my x system. Yep. You get 1044.92 dot 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 with 3 sig figs. It's 1040 grams of CaCl2. So if I circle some stuff, this box right here is this arrow right here. It's like, hey, it's 6.022. And then this arrow right here is this box right here. Because if you actually look at it, the 110.98 grams per mole, this is molar mass. But yeah, so that's pretty much it. You guys want another problem that you guys want to try yourselves or move on to Stoich? All right, yes it is. I wonder if I could copy paste this. Oops, that's not selecting. Stork. Copy. Paste. Oh, didn't work. So let's get rid of this problem. All right, what problem? Ready, set, go. Cheating, and some kids, it takes a while for them to like reschedule their tests after they've been absent or something. So I can't give out those quizzes just yet. if you ask for it. But we'll have a bunch of practice problems, review packets, and all that. Do this problem. Some people are already done. They're already typing their answers. I see them typing. Yeah. Kids have come before school, after school, say, hey, Mr. Lee, can I go over that test with you? And then we would go over the test together. Some kids just cry. Done with this problem? I never said a student's name. I just said generally. Dylan, focus, do this problem. No, Alec, don't say hi. Tell him to focus instead. Good job. Minus half off for units. Alec, come on. You know better. There you go. So let's do this one. So this one I have to go through the whole gamut. So I'm starting at grams and I want to end up at total atoms. So I have to go through 1, 2, 3 steps. So I have 55.55 grams of dihydrogen monoxide, which is what? Water, H2O. So then, first thing I want to do is get rid of grams of H2O and go to moles of H2O. And if I look here, going from grams to moles, I have to use molar mass. So this whole section right here is molar mass. So Mr. Mole is by himself, so it's a 1. And the mass of 1 mole of water is 18.02. So now grams of water cancels out. So now we're stuck at mole. So now I have to get rid of mole to get to molecule. So get rid of mole and go to molecule of H2O. Mr. Mole is by himself, so I could give it a 1. Then, as I traverse from mole to molecule, I have to use Avogadro's number. So this is where I go 6.022 times 10 to the 23rd, because I know that's how many molecules there are in 1 mole. So now I'm at molecule, and last step is to get to total atoms. So I want to get rid of molecule of H2O, and I eventually want to just go to total atoms, H2O. So now if you look at it, it says count the number of atoms in one of these. So, hey, in one molecule of H2O, how many total atoms are there? There's 1, 2, 3. 3 total atoms, molecule cancels out. So then you can multiply across, so it's 55.55 times 6.022 times 10 to the 23rd times 3 divided by 18.02, and you get 5. Ooh, I got a different number than Alec. 5.569180 times 10 to the 24th. And my number is more correct than Alec's. Ooh, you did forget something. So then with 4 sig figs, it's 5.569 times 10 to the 24th total atoms of water. That. No, no shortcut. This Mr. Mole Street, there's no shortcut. You have to drive through all of this. All right. Slowly getting there. 56 to an hour and 11 minutes. We talked about conversions. Next, Stoich is kind of like conversions. Well, yeah. We'll do mass percent first. Just because Stoich, pretty much I could use a Stoich problem to get you to write an equation, balance the equation, convert, and do stoichiometry. So one Stoich problem I could test for a bunch of different topics. So let's do mass percent first. Mass percent is pretty easy. If I wanted to ask you what is the mass percent of copper in copper to bromide? All you have to do is 100% times total mass of what you're looking for, divided by the total mass of whole thing. In this case, we're looking for copper. So you first have to figure, do you guys want to try this out? Should I just go through it? Try. Try it is. Do you guys all know each other? Or are you guys just talking on this chat? Yes. Nope. I know Michael. I feel like everyone knows Michael. Dylan, stay on topic. Done? What you get, Kyle? All right, let's go over this. Total mass looking for. So we're looking for copper. So hopefully you guys know that it's CuBr2. So there's only one copper and then CuBr2. Copper is 63.55 divided by 63.55 plus bromine is 70.90 plus 70.90. So that's going to be 70.9 times 2 plus 63.55, 63.55 divided by that. So it's going to be 63.55 divided by 205.35 times 100%, 0. Where'd you guys get 28.45? Is copper not 63.55? It is. Oh, 79.90. Good job, Emma. Extra credit. Some of you were starting to freak out that, oh my gosh, we got this wrong. But nope. What would you guys do without Emma? 63.55 divided by that. 0.2845 dot dot dot. 28.45% copper. Nice. Improvised. You mean improved hydrate question. Do you treat the mole amount like you do with empirical formula? Like, do you store the values and use the whole number say yes? So basically, never round until it's your final answer. So never round. How's percent composition? I should probably charge before it just randomly dies on me. Nice. So percent composition is hopefully not that bad. All you have to do is just, you guys all know how to find percentages. All right, so now let's talk about Stoich. 111 to 117 minutes. We talked about mass percent. 117 to something minutes. We'll talk about Stoich. Stoich problem. How many grams of? Can we just do a homework question? Well, you didn't ask for a homework question, so I'm going to make questions up. Remember, I don't have the homework in front of me. You guys got to type it. Nope. Type, type, type. Or else I'm going to make my own problem. Well, looks like I'm making my own problem. Just kidding. It's a stoichiometry. Stoichiometry just helps you go from one substance to another substance using the mole ratio. So it's like going from grams to moles. You guys all know how to do that. And then there's like molecules, formula units, and total atoms. So you guys know that. Then on the other street, there could be grams to moles, molecules, formula units, total atoms. So the story goes, Mr. Mole is inviting his family over, but he doesn't really like his family. So instead of them all coming over to his house, he creates their own streets, where on their own street, they have their entire own street by themselves. But since they're all part of the family, Mr. Mole and his relatives, they want to kind of see each other every once in a while. So the only thing connecting them is the mole. So now, so before we get to your homework problem, anytime you go between grams and moles, what do you have to use? So to go from grams to moles, you have to use moles? Indeed. Molar mass. And if you wanted to go from moles to grams, you would have to also use molar mass. The only different thing stoichiometry is now it's relating two different compounds together based on their mole ratio. Kind of. It uses the mole ratio. And then you're going to get the mole ratio based on the balanced chemical equation. That's going to allow you to jump from one street to the next street. So your question was, Let's copy paste that. Let's get this. I guess it has the same thing. Nice. There's that. And you have this. Second. Mole to mole. That one's the easy one. All right, we could do that one. All right, do this problem. So this stoichiometry is great because I could just give you this sentence and then say, all right, go do it. Something I might have to add though for this one is undergoes combustion. Now do it. So step one would be for you to actually make this reaction. You guys all have it in front of your homework, but then you're like, okay, ethane is C2H6. This one's a gas. And it undergoes combustion. So it's supposed to combustion. So that means I need to add O2, and it'll form CO2 gas and H2O gas. So that's one topic we've learned this unit, how to make these equations. So the second thing would be to do is balance. So I have 2 carbons, 6, 2, 1, 2, 2, 1. So I need to put a 2 in front of here. That becomes a 2 and a 4. You put a 3 in front of it here. That becomes 6 and 3. So that's good, that's good, that's good, and that's good. So now I have 7 oxygens, but 2 oxygens. So I'm going to throw a 7 over 2 over here. That changes that to 7 oxygen, so it's good. But then I have to get rid of my fractions. So then I multiply everything by 2. So now this becomes a 2, 7, 4, 6. Yeah. So that's balancing an equation. That's another thing we've learned this unit. Then a little thing that you might want to learn how to start drawing for stoichiometry is this. Grams of A to moles of A to moles of B to grams of B. This will help you where it's like, okay, molar mass, molar mass, molar mass, molar mass. Then this one is the special one where this one you have to use the coefficients. So in this case, I'm going from moles of ethane to moles of O2. So I'm starting off with 4.50 moles of C2H6. So before y'all start blasting answers, Andrew, I'm calling you specifically, what unit do I want to get rid of right now? Mole. Here's the problem. What unit do I want to go to? I also want to go to mole. So here's the problem now. If I just say, oh, I want to get rid of mole and I want to go to mole, you have to be a little bit more specific now, since now we're converting from one substance to the other substance. So which mole do I want to get rid of? Yeah, I want to get rid of moles of C2H6. So that's why I put C2H6 down here. And I want to go to moles of O2. At this point, if you actually look at this, I have a mole and another mole, 2 moles in the same box. 2 moles in the same box right here. So where do I get my numbers? I can't just show favoritism and give one mole the number 1 automatically. So where do I get my numbers? From the coefficients, from the equation. So my C2H6 is right here. The coefficient of this is 2. So I'm going to put 2 down here. Coefficient for O2 is 7. So it's going to be 7 up here. We are getting rid of the C2H6 because if you read the question, it's just saying, hey, we're basically trying to convert moles of ethane into moles of O2. So that means in order to get to moles of O2, we have to change moles of ethane into O2. So by getting rid of it, I'm just saying what's going to happen to my moles of C2H6 and my moles of C2H6. They're just going to cancel. What happens if you don't balance your equation? Are you guys going to get the right answer? No, it'd be more than a half off. Because if you don't balance, you don't get the correct coefficients. So that's why coefficients are important. No, you get the whole thing wrong. So 15.75 with 3 sig figs is 15.8 moles of O2. So that's all Stoich is. So then, a more usual Stoich problem would be if I gave you grams. So let's say using this same equation, I'm going to give you grams of something. So I gave you, I say, hey, I want to burn 23.0 grams of ethane. How many grams of CO2 will I produce? Ready, set, go. Is it really 15.8 grams CO2? Oh, Savannah. Should I do this? Are you guys all done? All right, I'm going to start doing it. So, we're starting with grams of substance A. So I'm starting here. What's the first step I have to do? If I eventually want to get here, this is the end goal. First thing I have to convert is from grams to what? Grams of A to moles of A. So then that means I need to get rid of grams of C2H6 and go to moles of C2H6. Mr. Mole is by himself in this case, so he could get the 1. And how do you find how heavy 1 mole of C2H6 is? You use the molar mass. Molar mass is 30.08. Grams of C2H6 cancels out. Now we're at moles of C2H6 right here. What's the next step? I'm at moles of C2H6. I'm at Mr. Mole's house. Where do I want to go now? Yeah, I want to go to mole B. I want to go to the next street over, which is a completely different street, but I want to go to that mole's street. So, Andrew, in order to do that, what do I have to use? You don't know. So let's talk about it. So first off, what unit do I want to get rid of in this case? Moles of what? Remember, you have to be specific. Yeah, C2H6. And which mole do I want to go to? CO2. So now I have 2 moles. So the only fair way to give them the numbers would be to go where to grab how many of each mole I need. It's kind of hard to tell, but this word right here is, yeah, the coefficients. So if I look at the coefficients of C2H6, what is the coefficients of C2H6? 2. So I put a 2 there. So for every 2 moles of C2H6 that I burn, how many moles of CO2 will I make? 4. Then my moles of C2H6 cancel out. Now I'm at moles of CO2. What will be my last step to convert moles into grams? In this case, Mr. Mole's by himself, so he gets the 1. Then 44.01 moles of CO2 cancel out times 2 times 23.0, don't need the 0.0 part, divided by 30.08, and you get, anyone have the answer? Anyone still here? Correct answer is, more numbers than I need, is 67.302 dot 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 3 sig figs, 67.3 grams of CO2. Muy bien. All right, with that, I'm tired. We were very detailed. We didn't go through as many topics, but we went through a bunch, around 35 minutes. So I stopped recording. Thanks for coming.